Now let us analyze a steady flow process. Now before we do that, let us first of all understand what do we understand by steady flow. Now there are two things whenever you have a fluid flow. So this is pertaining to a fluid flow in a particular system. So whenever we have a fluid flow, there are two things to be concerned about, and that is the rate of mass flow or the mass flow rate and the rate of energy flow. Now, so whenever a fluid flows through a certain control volume, its thermodynamic properties may vary along space and time. You can have the variation along space and time. Alright, now if the rates of flow of mass and energy through the control surface changes with respect to time. So we are not talking about the variation with respect to space. We are only concerned about, or we are only talking about or taking into consideration the change with respect to time. Okay, so whenever the rate of mass flow and the rate of energy flow through a control surface, it changes with time, the mass and energy within the control volume will also change with time. Okay, so it means that if the mass is a function of time, alright, in a particular control surface, then the mass will actually change with respect to time. So there will be a dependency of rate of flow of mass with respect to time. So the variation of mass with respect to time would be a non-zero quantity. So this kind of a flow, where the mass flow and the energy flow and any thermodynamic property for the fluid flow is dependent upon time, this kind of a flow is called unsteady fluid flow. Alright, and when we have the flow rates of mass and energy independent across the control surface, then the flow is called steady flow. This means that when we talk about constant mass flow rates, now this constant value of mass flow rates, or you can say energy flow rates, now this is with respect to time. Alright, so when you have this, then the flow is called steady flow. Now although you have the same flow throughout with respect to time, the flow might change at different locations. So you would have variation along the space coordinates. Okay, so in a steady flow, you would have dm or d energy by dt is equal to 0. This means the mass flow rate is not a property or is not a function of time, but the variation of mass flow rate with respect to any coordinate or space would be non-zero. So this is what we understand by the term steady flow. So the only thing to consider here is time. It might vary with respect to the space coordinate. Okay, so now after this, that is understanding or defining what a steady flow is, let's put our focus on this particular diagram that is drawn over here, and this is actually depicting a steady flow process. So you have a steady flow device over here, and we would actually analyze the mass and energy balance through this steady flow device. Now in this particular figure, you have a steady flow device in which one stream of fluid enters. So this is the fluid stream that is entering the device. So this is the inlet, and it exits or it comes out through the other end of the control volume. So this is the exit or the outlet. Alright, the assumption is that there is no accumulation of fluid mass within this steady flow device. So I would say no accumulation of mass within this device or within this control volume. And apart from this assumption of no accumulation, we also assume that all the thermodynamic properties within the control volume are independent of time. So this means it is a steady flow. Alright, so you have two sections. Let me move up a bit. Yeah, so you have one section as section 1 and the other as section 2. So let us say the area at section 1 is A1 and the area at section 2 is A2. The mass flow rate at section 1 is M1 dot and the mass flow rate at section 2 is M2 dot. Now the pressure at section 1, now this is the absolute pressure, this is not the gauge pressure, is P1, and the absolute pressure at section 2 is P2. Now the specific volume at section 1 is small v1 and the specific volume at section 2 is small v2. Next we have the specific internal energy, and that is small u1 here and small u2 over here, right? And the velocity of the fluid inflow is v1, capital V1, and the fluid outflow velocity, that is capital V2. And we have this line as our datum or the reference line, and this is an arbitrary datum, and from this arbitrary datum the elevation of section 1 is Z1 and the elevation of section 2 is Z2. Okay, now let us say that you have certain heat transfer through the control volume or through the control surface, that is dq by dt, and then you have certain work output. Okay, so that work output is through this shaft. So this is my shaft, alright, that is attached to the steady flow device, and you get some shaft work out of it, and this shaft work is nothing but dw by dt. So dq by dt is the net rate of heat transfer through the control surface, and dw by dt is the net rate of work transfer through the control surface. Okay, now after understanding the arrangement of this steady flow device carrying out a steady flow process, now let's go on to the first analysis and analyze the mass balance in this steady flow process. Now we are assuming that there is no accumulation of mass within the control volume. This means that the mass flow rate which is entering should be equal to the mass flow rate which is coming out of the steady flow device or the control volume. Okay, this means the rate of entry is equal to rate of flow of exit. Now this means that this is equal to A1 V1 by small v1, that is the specific volume, is equal to A2 V2 upon V2, that is the specific volume at section 2. This equation is known as the equation of continuity. This is known as the equation of continuity. Okay, so you should make a note of this, and this is the mass balance. Now let's do the second analysis of energy balance. Let's analyze the energy balance in this steady flow process. Now before we analyze the energy balance, we need to understand one very important concept, and that concept is of flow work, because we will be talking about flow work in the energy balance analysis of this steady flow process. Now what is this flow work? Well, if you have to define it, the flow work is significant only in a flow process or an open system. So I'll note it down, or I'll write it down and you can note it. So flow work is only significant in an open system or a flow process. Alright, in a flow process or an open system. So this is the very first point. Alright, and it represents the energy transferred across the system boundary as a result of the energy imparted to the fluid by a pump or by a blower or by a compressor Okay, so this is the flow work. Now flow work is analogous to the displacement work. Alright, and to analyze or to understand the flow work, let us draw a small diagram to understand it. So let us draw an open system. So this is how your open system would look like. Okay, so this is how it will look like. And let us draw a small, or you can say an imaginary boundary across it, and this would be your control surface. Okay, so this is the boundary. Alright, now let's assume that this is section 1 and this is section 2. Alright, let's put an imaginary piston over here. So we'll talk about this in a moment. Alright, and let me draw something over here and give it a different color. You would have arrows pointing in this direction. Alright, and this is a small volume that we talk about, and this is dV, and you have some mass entering over here, that is m1, and you have some mass which is coming out of section 2, which is m2, and this is the boundary of this open system. Now let us say that at section 1 the pressure is P1, the volume is V1, and the cross section area is A1, and at section 2 pressure is P2, volume is V2, and the cross section area is A2. Now let us say that this is an imaginary piston. This is an imaginary piston, alright, because we are trying to put it analogous to the displacement work, so that is why we are considering a piston arrangement over here. Alright, so this is an imaginary piston on which we have a fluid pressure P. So we have a fluid pressure P, okay, which is acting on this side of the piston. Alright, now this pressure is acting for this much volume of fluid, which is P, that is dV. Now the work done on this imaginary piston by this pressure as the piston moves forward, so that is dW. Now this is the flow work we are talking about. This is Pdv. Okay, so we take this much amount of imaginary volume, and let us say this much volume is dV, and this is exerting a pressure onto this imaginary piston over here, and this would create a work, that is the flow work, which is equal to Pdv. Now this is analogous to displacement work. Now what is this dV? I just told you it is an imaginary or a small volume element of the fluid, and this is about to enter the system. So this is, so when the fluid pushes it from this side, this much volume of the fluid would enter the system. Alright, now this means that the dW flow, alright, this is equal to P into small v into dm. Now this is the specific volume, so this means that d capital V is equal to this, that is change in total volume is equal to specific volume into change in mass. So you should make a note of this. This means that the workflow, or you can say the flow work, sorry, not the workflow, the flow work at inlet. The flow work at inlet. Now how much would this be? This would be dW flow, that because it's the flow work at inlet. This is equal to, now you have this as the work flow rate or the flow work. So this will be P1 small v1 into dm1. Okay. And similarly, if you find out the flow work at outlet, and that would be P1 P2 V2 into dm2. Okay, so these two equations are very, very important. Now if you find out the flow work per unit mass, so the flow work per unit mass, alright, that would be equal to dW flow, and this would be equal to PV. That's it, because this mass would become 1 and the value would become just PV. So flow work is equal to PV, and displacement work is equal to PdV. So this is the value or the difference in formulas of flow work and displacement work. Now if you go back to the steady flow device we were discussing earlier, that is this, alright, you have this as the work output, that is the shaft work output, and you would have a certain component of flow work at section 1 and at section 2. Let us say this is the work which I denote as Wx, or because it's a shaft work I would give it a name Ws. So Ws is the shaft work, and you would have a certain component of flow work at section 1 and at section 2. This means that the total work transfer is equal to Wx is the work that comes out of the system as the shaft work minus P1 V1 dm1 plus P2 V2 dm2. Now you would understand from where did we get this particular equation, because this is the flow work at inlet. Why minus? Because you had to push in the fluid at section 1 in the diagram. So here you are pushing in the fluid, so the work done is negative, and at the outlet you are the fluid is actually moving out on its own by doing some work inside, so the work done is positive over here. Now the equation now gives us the total work done or the total work transfer. Now if I differentiate this with respect to time, I would get it into the rate form. So I would get dW by dt is equal to dWx by dt. Now because work is an improper integral, so you would put a dash on top, okay, minus P1 V1 into dm1 by dt, alright, plus P2 V2 into dm2 by dt. So this is what you would get. Okay. Now this dm1 by dt, this is the mass flow rate at section 1 and this is the mass flow rate at section 2. So this is m1 dot and this is m2 dot. So the equation would become d dash w by dt is equal to d dash wx by dt minus P1 V1 into m1 dash plus P2 V2 into m2 dash. So this is the equation that you get after understanding the concept of flow work. Okay, so this is the total work flow rate or the work transfer rate, I would say, across the boundary. Alright. Now, since there is no accumulation of energy inside the system, so by the conservation of energy, the total rate flow of all energy streams entering the control volume must be equal to the total rate of flow of all energy streams leaving the control volume. So this would take a shape of something like this. So total energy in should be equal to total energy out. Alright, so this should be your equation. Now, the total energy in, so let us say that you have two quantities E1 and E2. Now, what are E1 and E2? Well, E1 and E2 refer to the energy carried into or out of the control volume with 1 kg of the fluid. So this is the energy in per kg of fluid and energy in per kg of fluid, and this is the energy out per kg of fluid. Alright, now if I have to write the equation, the total rate of energy in flow would be equal to the mass flow rate at the inlet into the energy inlet per kg plus, now you are actually putting in the heat. So if you look at the diagram, the total heat transfer is dq by dt, that is going into the system. So you would write down plus d dash q by dt is equal to m2 dot E2, that is the energy outflow rate, plus dw by dt, that is this. So this is the work that we are getting out of the complete system. Now put in the value of this from this equation. So we would have m1 dot E1 plus dq by dt is equal to m2 dot E2 plus dwx by dt minus, you would have p1 v1 m1 dot plus p2 v2 m2 dot. So this is what you would get. Okay, now bring the values with suffix 1 on the left hand side and keep the values with suffix 2 on the right hand side, and we would get m1 dot E1 plus p1 v1 m1 dot, alright, plus dq by dt is equal to m2 dot E2 plus p2 v2 into m2 dot plus, let me rewrite it, plus dwx by dt. So this is a very, very important equation, just note it down in this analysis. Okay, now if you look at E, now what is E? E is basically the specific energy. Now the specific energy, if you remember the video we did on control volume, the specific energy was E is equal to, let me use some other color, so E was equal to the kinetic energy plus the potential energy plus the residual energy, isn't it? So kinetic energy per unit mass is v square by 2. The potential energy per unit mass is elevation into gravity, and this remains u. So this is a very, very important thing to remember over here. And then you can put the suffixes 1 and 2, and you would get, if you put these values in this equation, okay, the equation now would become, you would get the value. So you can take m1 common, so you would have m1 dot common, and we would have v1 square by 2 plus Z1G plus U1 plus P1V1, alright, plus dQ by dt. So this is the total energy at the inlet. Alright, now let's equate it. Then you would have M2 dot into V2 square by 2 plus Z2G plus U2 plus P2V2 and plus dWx by dt, that is the rate of shaft work out of the system. Okay, now we all know that U plus PV is the enthalpy, so this becomes H1 and this becomes the enthalpy at the outlet. Alright, and this would now take the shape of M1 dot into V1 square by 2 plus Z1G plus H1 plus d dash q by dt is equal to M2 dot into V2 square by 2 plus Z2G plus H2 plus this. Now I know it is getting a bit boring, but if you understand this complete analysis once, you would never forget it in your life. So doing this once is very, very important. Okay, now we just saw, or we just analyzed that, as per the mass balance, M1 dot, this is equal to M2 dot, isn't it? So M1 dot is equal to M2 dot. Okay, and let us say this is equal to M dot. So this means this is equal to dm by dt. This is equal to dm by dt. Now, if I divide the whole equation by dm by dt, then we would get v1 square by 2 plus z1g plus h1 plus the change would be here, you will have dq by dm. Now this is the heat exchange per unit mass. This is equal to v2 square by 2 plus z2g plus h2, and then you would have the work done per unit mass. This equation is what we need to derive, and this equation is called the steady flow energy equation. This is called the steady flow energy equation, and this is a very, very important equation when you apply first law to flow processes. Now basically you have two SFEEs, that is, you have two steady flow energy equations. So one is this and the other one is this equation. This equation is also a steady flow energy equation, but there is a very minute difference in both the equations. So this is also your SFEE. Let us say this is equation 1 and this is equation 2. Now in SFEE 1, the terms, so all the terms in this term, this term, this term and this term, all the terms, they represent energy flow per unit time. Okay, so in this particular equation, that is SFEE1, all the terms are in joules per second or kilojoules per second, that is energy flow per unit time. Okay, but in SFEE2, all the terms represent energy flow per unit mass of fluid, so that would be joules per kg. So this is all that we have to understand in this analysis of steady flow processes. Now the steady flow energy equation applies to a wide variety of processes like pipeline flows, heat transfer processes, mechanical power generation in engines, and so on and so forth. So now in the next set of videos, we will talk about the examples of application of this SFEE equation, and we'll start with the first example of its application, that is, we'll apply the SFEE on nozzle and diffuser.